Okay. Good evening. Week 3, Thursday. Today we're going to do a different topic now, and this topic is known as normal stress induced by bending moment. And this topic is a different topic, but it's nothing new. Okay, you guys should have learned in your prerequisite course, which is 2P04. So I'm going to go through a very quick, so-called revision. Okay, and some things might not be clear to you when you're learning it for the first time. Okay, and I want to clear your doubts on this topic. Okay, right. So there are four different types of. Okay, so there are four different types of bending moment or bending moment induced stresses. Okay, so the first one, which is very common, okay, we call it centric symmetrical bending. And the general formula for symmetrical, I'm just going to write out the general formula. So this is normal stress in the x direction is equal to minus mz over izz multiplied by y. Okay, and this were to follow transformation, where this is our x direction, y, and this is rotation about z. The second type is what we call eccentric. Okay, so it's like buckling. You got centric and you got eccentric. Okay, and if you look at buckling, is stresses induced by bending moment, isn't it? Right? Once you start to buckle, you have a bending moment, right? So you have eccentric, symmetrical, bending. So the difference in this is one is centric, the other one is eccentric. Okay, both are still symmetrical. So over here you have stress x. Now again, this is a general formula. Okay, so now you have px over a minus by mz over izz multiplied by y. So the only difference under eccentric is you have axial. Okay, so this is axial loading. Okay, so the third type is very commonly seen, and I'll write down the associate formula is what we call centric. Now it comes to be unsymmetrical. Okay, unsymmetrical bending. So this is where again you have stress x. Now you have bending moment acting about two axes. Okay, so I'll write down minus mz over izz multiplied by y plus by my over iyy multiplied by z. Okay, so the difference between symmetrical, okay, let me choose a different color. The difference between symmetrical and unsymmetrical is symmetrical, you only have moment applied in one axis only. So for this case, is moment about Z. Okay. When it's unsymmetrical, we have moments applied in two axes. I.e., over here you have MZ and you have MY. Okay. And the fourth type, as you can guess, is what we call eccentric, unsymmetrical, bending. And the associate formula is stress in the x direction. Again, you now have px over a minus mz over izz multiplied by y plus by my over iyy multiplied by z. Okay, so the only difference now between, again, you know the difference between eccentric and centric is now we have an axial load. Okay. Right. So these are the formulas. Okay. Now, in my course, I don't want you all to worry about the signs over here. I don't want you all to worry about negative and positive. Okay. You can see they are negative and positive down here. For this course, I don't want you all to memorize whether is it negative or positive. Rather, I want you all to visualize. Okay, because if you can visualize, okay, then it'll be so much easier and you will be less confused. Okay, now let's look at centric bending. Okay, so let's look at the first type, which I'll go into more detail. We have centric symmetrical bending. So in this case, if we have a transformation over here, okay, so this is our x, this is our y, and this is our rotation about z. Then we have a beam, a simply supported beam. One side is pinned, the other side is on a roller. So right down here, this is pinned, and down here is on the roller. And you guys should know the difference by now. And then you have an applied load at the center. Okay, E. And then with this applied load, we have the associated distances. This is L over 2. And then here to here, this is our L over 2, right? So the formula that we're going to use, okay, or rather than thinking about the formula, I will sketch out the deformation pattern. Okay, so the deformation pattern, once the load is applied, the deformation pattern in, I'm going to draw in red, will look like this. All right, this is the deformation pattern. And the moment will look in this direction. right? So this is moment Z axis, moment about Z axis. So for this case, the formula we're going to apply is stress in the x direction. The normal stress is in the x direction is equal to minus mz over izz multiplied by y. Okay. So why they have this minus sign down here? Okay. So if you look at this the diagram over there, right? I'm going to draw at a certain point. Okay. This dot I draw is the center of curvature. Okay. For the or I don't need to put a bracket for the deformation pattern. Okay. Now let's look at the deformation pattern. And I'm going to call this point over here point A, right? At the center where the force is applied at our point B, and the last point over at point C. And we are aware that failure will occur at point B. Okay, failure will occur at point B. So that's why we calculate our stresses all at point B. And at point B, I'm going to introduce two more points. The top over here, I call point alpha. Over here, I call point beta. Okay, that's our point alpha and point beta. And then I'm going to sketch, a green line. Yeah, I'm going to sketch a green line, and you all should know what this green line is all about. Oops, go on. I'm going to sketch a green line now. And this green line is our centroid. And we know that the centroid is a geometric centroid. Okay. And relative to the center of curvature, right, any point above the centroid, towards the center of curvature, y is positive. Away from the centroid, okay, or away from the center of curvature, from the centroid, y is what? Negative. Right? Okay. So why do we do that? Okay. But before I explain why do we do that on the formula, okay, if you look at point beta, right? So after deformation, or point alpha, after deformation, at this point over here, this is our alpha prime dot. Over here, this is our beta prime dot. Okay. So after deformation, you realize that alpha prime is under compression. Because the radius of curvature is smaller and point beta smaller relative to the centroid, okay? And beta, right, is under tensile. As you can see, okay, it's under tensile. So when that's the case, right, when we go back to this formula, okay, so we know, based on the deformation, we know that alpha is under compression, beta is under tension. So now if we were to look at this formula, okay, so if we were to look at point alpha, right, y is what? Positive. So from here, we know that stress x at point alpha is equal, if we apply the formula, we're equal to minus mz over izz multiplied by positive y.